All right. Get my stream set up here. All right, I just wanted to hop on here for another hour just to get this shared memory chapter done. We're almost through it. There's about 15 pages, I think, left on it. So, yeah, I just want to get that done, and then I'll go in and clean up all the Git repo stuff before I sign off for the evening. All right, so it is page 1001, and it is 627. All right. Example transferring data via shared memory. We now look at an example application that uses systemd shared memory and semaphores. The application consists of two programs, a writer and a reader. The writer reads blocks of data from standard input and writes them into the shared memory segment. The reader reads blocks from the data from the shared memory segment to standard output. In effect, the program treats the shared memory somewhat like a pipe. The two programs employ a pair of systemd semaphores in a binary semaphore protocol. Init semaphore available, init sem in use, reserve semaphore, and release semaphore. Functions defined in section 47.9 to ensure that when one process accesses the shared memory segment at a time, and the processes alternate in accessing the segment, i.e. the writer writes some data and then the reader reads some data, then the writer writes again, and so on. Figure 48.1 provides an overview of the use of these two semaphores. Note that the writer initializes the two semaphores so that it is the first of the two programs to be able to access the shared memory segment. That is, the writer semaphore is initially available and the reader semaphore is initially in use. Source code for the application consists of three files. The first of these, listing 48.1, is a header file shared by the reader and writer programs. The header defines the shared message structure that we use to declare pointers to the shared memory segment. Doing this allows us to impose a structure on the bytes of the shared memory segments. Okay, so we got a writer process which reads from standard in, writes to the shared memory. So it's going to reserve the semaphore, copy data from standard in to the memory, then release it over and over. Reader process is going to do the same on its end, or the inverse of that on its end. We have buffer size of 1024. The write semaphore and read semaphore. Okay. And then this is the structure. So you have count, which is how many bytes were written into the buffer, and then the buffer itself. Okay, that makes sense. So this program performs the following steps: create a set containing two semaphores that are used by the writer and reader program to ensure that they alternate in accessing the shared memory segment. I don't know why you need two semaphores. I guess to guarantee that you can alternate, but who cares if you're guaranteed to alternate? I guess that is a nice property to have. But you pretty much get somewhat of a guarantee, not a solid guarantee, I guess. Okay, so they create two semaphores to get a guarantee that they alternate. The semaphores are initialized so that the writer first has access to the shared memory segment. Since the writer creates a semaphore set, it must be started before the reader. Then it creates the shared. You know what? I'm just going to read the code because I don't like reading people's textual descriptions of code. I'd rather just read the code. So we have semaphore ID as well as a shared memory ID, some bytes in an integer, and XFRS integer. We have our struct, which is a shared memory segment pointer, and a union of semaphore union dummy. Okay, that's pretty much all the stack stuff that we have here. So we say I'm gonna do the semaphore get, on a size 2, create it, and here's the permissions. So it's get or create. And then we initialize the semaphore on the right side. And then we there's initial semaphore available, and just init semaphore in use. Okay. So the read is currently in use. The write is not in use. That's weird because the writer is supposed to go first, right? We then do a shared memory get. So shm seg. This guy here is going to be our shared memory segment. We do the same thing, IPC create with some object permissions. I've learned that you don't even need to give this flag for it to create it. You then attach the shared memory wherever, it doesn't matter. And then it looks like FRS bytes. And then we increment FRS every iteration. And we increment by count on the bytes. So bytes is a running total of how many bytes have been written. XFRS is how many times we've performed the write. We reserve the semaphore on the right, and we then perform a read on standard IO, and then we release the semaphore for the read. Wait a minute. Reserve the semaphore for the write. We read into the buffer. Okay, so we're just saying like read straight to the buffer. Even though this is a write operation, we're reading from standard input and we're writing to the buffer. Reading and writing is always like this, like, it's confusing because every read is a write and every write is a read. Because in order to read, you have to write. In order to write, you have to read. So yeah. We then release the read end to allow the read to continue. So the read was blocked first. Not because we were reading, but we wanted to prevent reads from happening. And then we acquire the write, which prevents reads. So at this point, reads and writes are not happening. We then perform our write into the buffer, the shared buffer. And then we release the reads to allow the reads to continue. And then we check for EOF. If we hit EOF, then we try to acquire the write. Once we have the write end, then all the reads have completed. And we can then remove the semaphore. We can then detach the shared memory and remove it. And then we're done. And then the reader, so this is going to be the reading side. So I'm just going to read through this code. We do a get on the key. It should already be existing. Same thing with the shared memory. We then attach the shared memory as read only. We don't want to do any writes to it. And then we reserve the reading side of the semaphore. And we then increment the bytes, and we read the bytes to standard out. Or write the bytes to standard out, I should say. And then we release the write end to allow writes to continue. So now reads are blocked as well now. So it kind of, I think he could have implemented this as a single mutual exclusion lock, but the problem is that it would not guarantee the alternating between the reader and writer. So that's why he has two semaphores and orchestrated it this way. Because you could have the writer reacquire the lock. What I would have done is just like use a single mutual exclusion lock, and then have if the writer just wrote and it continues writing again, like either put it to sleep or have it otherwise yield to the kernel immediately. Like detect that you've already done your write and yield to the kernel, yield back to the kernel. And then hopefully the kernel will schedule the reader, and then the reader will acquire the lock. But that's kind of like not as optimal from an instruction perspective. You have a lot more going on there computationally, whereas this is much more elegant with guaranteeing alteration between reader and writer. And then it just says, hey, I'm going to detach from the shared memory, and then I'm going to reset my semaphore, and then I'm exiting. I'm done. So yeah, that's a nice little program, set of programs there. The following shell session demonstrates the use of programs listing 48.2 and listing 48.3. We invoke the writer using file etc services as input, and then invoke the reader directing its output to under the file. Yeah, so we send etc services into the writer, and then we say, hey, reader, read everything to out. And then once it's done, we can then diff etc services with out into the same file. The diff command produces no output, indicating that the output of the file produced by the reader has the same content as the input used by the writer. Location of shared memory and virtual memory. So this is something that I really wanted to spend some time with. In section 6.3, we considered the layout of various parts of the process in virtual memory. It is useful to revisit this topic in the context of attaching System V shared memory segments. If we follow the recommended approach of allowing the kernel to choose where to attach shared memory segment, then on the x86-32 architecture, the memory layout appears as shown in figure 48.2, with the segment being attached in the unallocated space between the upwardly growing heap and the downwardly growing stack. So let's just go over there. So the stack goes down, the heap goes up, shared memory just gets attached somewhere here. To allow space for heap and stack growth, shared memory segments are attached starting at the virtual address with a bunch of zeros. Mappings and shared libraries are also placed in this area. There is some variation in the default location at which shared memory mappings and memory segments are placed, depending on the kernel version and settings in the process rlimit stack resource limit. The address for blah 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 is defined as the kernel constant task unmapped base. It is possible to change this address by defining this constant with a different value and rebuilding the kernel. A shared memory segment or memory mapping can be placed at an address below task unmapped base if we employ the unrecommended approach of explicitly specifying an address when calling sharemat or mmap. Using the Linux-specific procpid maps file, we can see the location of shared memory segments and shared libraries mapped by the program, as we demonstrate in the shell session below. Starting with kernel 2614, Linux also provides the procpid s maps. Oh, what is this thing? I haven't used this before. Proc self s maps. Interesting. So it looks like we get the address range and then some properties like this is read and execute. P might be protected. Not sure. Not sure what these numbers are for, or these. Size. And then some VM flags. Okay. And then this is the thing that's being mapped in the file. Where is the VDSO? Here's VDSO. So it's mounted, or it's mapped as read and execute, obviously. Cool. So the smaps file, which exposes more information about the memory consumption of each of a process's mappings. For further details, see proc manual page. I think I'll hold off on that. Virtual memory address, argv environ stack goes downwards. Bottom here, text program code, initialized data, uninitialized data. PSS, heap. Heap goes up. Heap is actually implemented in most allocators now as memory mappings. So this program break doesn't go up. Okay. In the shell session below, we employ 3 programs that are not shown in this chapter but are provided in the SVS System V shared memory subdirectory in the source code distribution for this book. These programs perform the following tasks. Creates a shared memory segment. So we're going to take same command line, okay. Attach, RM. So these are the programs I've implemented myself, although I'm sure theirs are way better. So we begin shell session by creating 2 shared memory segments of different sizes. We then start a program that attaches these 2 segments at addresses chosen by the kernel. So you say, hey, map those in. The above output shows addresses with segments are attached. Before the program completes sleeping, we suspend it and then examine the contents of the corresponding proc PID maps. And we can see that, hey, we got those attachments there in the maps. And the output from proc PID maps shows a listing 48.4. We can see the following. Three lines for the main program, SHM attach. These correspond to text and data segments of the program. The second of these lines is for read-only page holding string constants used by the program. 2 lines for the attached System V shared memory segments. Lines corresponding to the segments for 2 shared libraries. One of these is the standard C library. The other is a dynamic linker, which we described in section so-and-so. A line labeled stack. This corresponds to the process stack. A line containing the tag VDSO. This is an empty entry for the Linux gate virtual dynamic shared object. This entry appears only in kernel since 2612. See Linux gate for further information about this entry. I'm curious, very curious. Oh, I don't want to go direct. Linux gate. Let me just copy this URL. Can I copy? Linked address. Let's do archive.org. Let's go way back. Back into time. Yep, live again. So let's just go back maybe here. Or I could go back over all the way to 2005. I wonder if this is in archive. That is. Yeah. 12 years ago. I didn't even know archive.is went back 12 years. Linux Gate SO. When you see the LDD utility reasonably recent, I gotta read this. This is on my reading list. Scatter Gather Thoughts by Johan Peterson. What was the name of the... Is he still like active? Not comedian. Okay. Wayback Machine is too slow. All right. The following columns are shown in each line of procpid maps in order from the left to the right. So if we cat out proc self maps here, then we can follow along at home. So a pair of hyphenated separated numbers indicating a virtual address range, obviously, in hexadecimal, at which the memory segment is mapped. The second of these numbers is the address of the next byte after the end of the segment, obviously. Protection and flags for the memory segment. That's what I was mentioning before. First three letters indicate the protection of the segment. Read, write, and execute. A hyphen in the place of any of these letters indicates that the corresponding protection is disabled. The final letter indicates that the mapped flag for the memory segment is either private or shared. So yeah, everything's private. For an explanation of these flags, see the description of the mmap private and mmap shared flags, section 49.2. So the book, when they showed their stuff that was attached, you can see it says S instead of P. Hexadecimal offset in bytes of the segment within the corresponding map file. The meaning of this in the following two columns will become clear when we describe the mmap system call, chapter 49. For the system V shared memory segment, the offset is always 0. So I think what happens here is you got the cat binary, and it's mapped into all these different locations, but you can see these offsets are different. And I think some of that is like ELF garbage that you have to offset past, but like some of it is also like, well, these are different sections of the ELF binary, and you need to offset to different places, and it's not, you can't just like plaster the entire thing right into memory and just run with it. It's like these things have to be mapped in different locations, and the offset defines where in the file that you are mapping, and this is the address that you're mapping it to, and then the end address defines the length. So you only need one number here. You don't need a second number because it's bounded by the length here. Let's see. The device number, major and minor IDs of the device on which the corresponding map file is located. So these are device IDs, major and minor. The inode number of the map file. Okay. Or for system V shared memory segment, the identifier for the segment. So if you go back up here, these are the segment identifiers. That's a very high number. I would have thought it would have been lower than that, but it is what it is. And finally, the file name or other identifying tag associated with this memory segment. For system V shared memory segment, this consists of a string system V concatenated with the shared memory get key of the segment expressed in hexadecimal. In this example, system V is followed by zeros because we created the segment using the key IPC private, which has the value 0. The string deleted that appears after the sysv field for system V shared memory segment is an artifact of the implementation. of shared memory segments. Such segments are created as mapped files in an invisible tempfs file system and then later unlinked. Shared anonymous memory mappings are implemented in the same manner. We describe map files and shared anonymous memory mapping in chapter 49. So far, this is the best API and implementation of IPC stuff in all of System V, because it's basically just doing memory mapping. So storing pointers in shared memory. Each process may employ different shared libraries and memory mappings and may attach different sets of shared memory segments. Therefore, if we follow the recommended practice of letting the kernel choose where to attach the shared memory segment, the segment may be attached at a different address in each process. For this reason, when storing references inside a shared memory segment that point to other addresses within the segment, we should use relative offsets rather than absolute pointers. For example, suppose we have a shared memory segment whose starting address is pointed to by base address, i.e. base address is the return value of this attach. Furthermore, at the location pointed to by P, we want to store a pointer to the same location as it's pointed to by the target, as shown in figure 48.3. This sort of operation would be typical if we were building a linked list or a binary tree within the segment. The usual C idiom for setting star P would be the following. Target is equal to star P, place the pointer in P. But that doesn't work because the addresses are going to get all messed up when you map it in next, when you attach it the next time. So we have our base address. I don't like that it's going up because addresses. Okay, yeah, we can visualize it this way. So we have P, which is a pointer to some target, and then its value is the memory address where the target is at. But that's according to the global virtual address space of this particular process. And what you really need to do is say, I want to go based on base address, add this many bytes to get to the target, which is not the same. The problem with this code is that the location pointed to by target may reside at a different virtual address when the shared memory segment is attached in another process, which means that the value stored at P is meaningless in that process. The correct approach is to store an offset at P as in the following. Yeah, so we just take the target and we subtract off the base address and store that. When dereferencing such pointers, we reverse the above step. We take the base address and we add the pointer of it. Add the offset. Here we assume that in each process, base address points to the start of a shared memory segment. i.e. it's the value returned by attach in each process. Given this assumption, an offset value is correctly interpreted no matter where the shared memory segment is attached in a process's virtual address space. Alternatively, if we are linking together a set of fixed size structures, we can cast the shared memory segment of the part of or a part of thereof as an array, and then use the index numbers as the pointers referring to one structure to another. That's pretty cool. I want to implement that. So let's go into chapter 48 here. And if we go here, I want to say, let's copy off the shared memory right, and let's call this thing pointers. So Vim shared memory pointers. So we don't care about this value anymore. We'll say base is at that, and result will be base. Base. Okay, so we got our attachment, and what we want to do is read the value at the pointer and then write a new value to the pointer. To the location targeted by the pointer, I should say. So when we want to read, it would be like int foo, and we're going to say foo is equal to the base. Wait a minute, we're reading, yeah, so we have to say base plus the value at p if p is not equal to 0, because the first time around p is going to be equal to 0. So p is going to be we'll just say integer. We can make it a void star. Why not? Void star p. And we say if p is not equal to null, then we do our stuff here. We have to assign p though. So p is going to be equal to result, or this would be base sub 1. No, sub 4. 0, 1, 2, 3, and then 4, since it's 64-bit address, and we want to be 64-bit aligned. So base sub 4, base is a char star. Income integer to pointer conversion. Well, we'll just say it's a char star then. Does that work? Why does that not work? Base is a char star. I'm just gonna make this a void star anyways. Void star. Void star. Assign 2 void star from incompatible type void. Oh, because the base 4 does a dereference. Yeah, because we want dereference base, go 4 bytes ahead. No. Base has to be a char star for us to do that. Char star. Char star. Oh, yeah, that's right. Okay. Let's leave it as a void star. We'll go 1 here. And we'll say base plus plus. There we go. Do some pointer arithmetic. So now we're 1 pointer off, so 4 bytes off of the base. And then we say, hey, if that is null, then, well, if it is null, I just want to handle that up front. We'll say printf p is null, not reading. Else, we'll attempt to read. I need a new line here and a semicolon. So we're going to attempt our read. So our read is going to be the base so trying to visualize this. So P is 4 bytes off of base. That's where we're going to store our pointer. So the type of P is a pointer. So we say if it's pointing to null, then it's null, we're not going to be able to read. Else we attempt to read by saying, hey, take B plus the dereference of P. And because base is a void star, and P dereference we have to cast this to be an int, I think. So say, hey, P, you're going to be a integer or a char star. And the void star here is going to have to be a char star. I still can't add char star and char star. Can I just say, hey, integer? You're an integer. Unsigned int, uint. Uint 64. Uint 64t. Uint 64t of base and p. So we add those together. That gives us a pointer. And then we can dereference that whole thing if it's a void star. Or let's just say like a integer star. Yeah, that'll work. And then we can print it out. Okay, so we say value, current value at P is going to be %d, and we'll say foo here. Okay, so that's the read. And then we're going to try doing a write here. So our write is going to be, I'm just going to printf writing. And we'll do a value here. We'll say value is argv2. And then we'll say writing to star p, the value value. Okay, so now we got to do this write. Okay, so the write is going to be, we're going to have to take the base. How do we want to do the write? I think we could do the same expression here. Just do a write, because this is the L value. And we could say, hey, you're going to be equal to value. I don't think that'll work. I need a star here. Expression is not assignable. Okay, let's save this off as an int star. We'll just say int star temp is equal to this thing. And then we're going to say, oh, we need a P at the end here. And then we'll say, hey, temp, we're going to dereference you. I don't know if that's going to work. I get the feeling that this is not going to work. This is where like my pointer math stuff is not great. So we have to store the pointer itself. So P is there. We're not storing the pointer anywhere. We're reading off of it here, but we're not storing it anywhere. So say we're going to go like 64. So P is equal to 64 here. And we'll call this a void star. Okay, so we're writing this 64 bytes off from, or let's just do 8. I don't want to get too far away. Maybe do 16. 8, what's in between 8 and 16? 12? Yeah, let's do 12. So we're 12 bytes off. Okay. Here we go. That's where we do the P. We don't need to assign it in here because we read it up here. It was P. So we have our base address, which is where we attached the shared SHM to. We have base plus 4, or base base at 0 is going to be storing temp value, test value, I should say, test value. Base at 4, we'll say this is a 64-bit aligned pointers based off of base. And then we have the dereference of base at 4. And this is the storing of test value. Okay. So in this situation, base is obvious here. Void P. Is this 0 initialized? So I could just initialize this in single expression. So we say, hey, base, you're going ahead 64 bits, which is, 64 bits is 8 bytes. Sorry, my math is wrong here. 8 bytes. 8. Okay. So here I'm going to printf out the pointer as well. We could say P itself goes there. So that should be either 0 or 8. And this needs to be so we'll say 16. And then that's if it's null, we initialize it basically. If it's already been initialized, then we know it points to 16, and we can do a read of the value, which should just be a dereference of P, right? I'm doing all this crazy stuff, but no, it can't be a dereference of P because it's literally the value 16. That'll be a segmentation violation. So we have to add on to P the value of the base. And to do that, we casted both of them, we casted them both to uint64t's. And then we casted that whole expression as an integer star and then dereferenced it to give us a copy of whatever was there. And then we printed it out. I'm going to call this temp instead of foo. Okay. Then down here, we're going to write to it. So we have to do a similar bit of math here. To get the address, we say, hey, grab the base, add the pointer. It's an integer pointer. And we're going to call that thing temp. Can we call this thing temp2? I guess this is scope. Okay, so we'll call it temp. And then we're going to dereference that thing and assign the value to it. I think that works. Yeah. Okay. Let's try that. Make. I doubt I'm going to get this on the first try. Build. Actually, if we do IPCs, we have a value already at this. One thing I want to do is output a bunch of the bytes as hexadecimal. So the shared memory pointers, I'm going to do that up here as well. I'll create a function. Actually, you know what? I'm going to use, I have a void star. Give me a function that prints out the first, let's see, we want $24. Let's just say 32 bytes as hex in C. And we'll paste that bad boy there. And then here, I'm just going to call that, once I have base, I'm going to call that here dump hex 32 of base. And then I'm going to do that again over here at the end. Okay. Let's make build, or let's do our IPCs. And then I'm going to say, hey, build shared memory write. And I have to give it a value and the ID. So I'm going to say 15. It said pointer and just died on me. Oh, that's just writing it. Okay. I want shared memory. And this is going to be pointers. Okay, we got a segmentation fault. What's interesting is like this write did not work. Can I do a read? Build shared memory attach 7. It was able to read it. So where's my 15 at? I don't see 15 here anywhere. It should be the first byte. Something's going wrong there. Let's start debugging. Get out of there. Vim. So why working with email servers is very hard, and I never get how come Google always gets best delivery and never gets their IPs banned. Yeah, I don't really know much about email address stuff or email stuff, SMTP. Try to stay away from all that stuff. Shared memory, pointers. I just want to dump the hex and actually see my output the way it should be. So we give it base, which is a void star. It takes in that and then iterates over it. Casts it into a char star. And then it iterates over that for 32 values, printing each one out. I should see my value in that. Make build shared memory. This will be pointers. I have to say 7 here. And I have to say, what, like 15? Let's try and attach again. What? The first byte is 15, but it doesn't show up in my output here. So annoying. So clearly I'm not attaching to it correctly. So attach. Oh, because I have it as read only, maybe? No. I didn't. I only did that on that one. Pointers. So let's look at what's going on here. So we have attach ID null 0. I'm gonna do, oh, because is this segment, so we have base and P here. Base and P should be the same value, right? It should be 8 bytes more. All right, we'll get those, and then we'll get a char star here called adder. Base will be converted into the char star. We don't care about the pointer, but the first byte we do care about. And then dumping from base, we do care about there. Okay, let's do a make on that. And then we'll do our build pointers. Now it's saying first byte is 0. And it didn't even do my pointer arithmetic right. Oh, because base was incremented. Oh, I'm so silly. What I have to do is say pointer is equal to base, and I have to say P plus plus here. Okay. Sorry, I'm really like old. I'm rusty on my C point arithmetic. There we go. Now we got it. The pointer is now 1 off. Yeah, okay, it makes sense. Okay. But that's only 1. I want it to be 8. I thought this would carry, I thought P++ would increment it by 8, right? We'll say in C, when you output the pointer value using %P, is that the actual numeric value of the pointer, or is it the is that the actual numeric byte address of the pointer? Okay. So we're going to say base that, base D, and then we'll say you're just going to be an integer, or a uint 64 underscore t. And then we're going to see what the difference is between these. This will be D, LD? Yeah, LD. And then this will be a, oops, a uint 64t. See, that's only going 1 byte off. That's my problem there. I need to go When doing pointer arithmetic, can't spell that word. Why does void star, does doing a plus plus on a void star only go 1 byte forward versus 8 bytes? The size of the pointer. Oh, and there is no pointee size of void. Well, we can fix this, say plus equals 8. That'll fix that. So we go from 72 to 80. Yeah, that's right. Although these aren't, yeah, these aren't 64-bit aligned. I don't think that doesn't look 64-bit aligned to me. Python, I do that, let's say divided by 8. Okay, looks like it's even. If I'd mod 8 it, 0. Okay, it is 64-bit aligned. Okay. So we don't need this anymore, don't need that anymore. We don't need the first byte anymore. We're going to dump though. I'm going to pull this up here because this helped me calculate things. Alright, and then if we make and build pointers 7, 1, 2, 3. Okay. Okay. So 8, we have the first 8 bytes that's reserved for the other testing. Second 8 bytes is the pointer. Third 8 bytes is garbage. We're going to skip that value. And then the last 8 bytes will be the target value. So this will be base plus, I'm going to say, I think add's a good expression. Base at 8. And then this will be base at 24. Like that. So in here, now we can do some of these things. We're going to say, hey, you're going to be 24 off. And that's fine. Okay. Okay, we got a core dump. So you got the current value at P is a bunch of garbage. And writing to P 1, 2, 3, we shouldn't have even gotten there because these are all zeros. So that means my point arithmetic here is wrong. I think I don't have to do that. I can just do P here, right? Because I've already. Oh, okay. So P literally has to equal 8. I can't compute that based off of base. So P will be. This is tricky. We'll call this LP because this is a local pointer. I think P's fine, but what I have to keep in mind is P is just a stack pointer. So I'm not testing if P is equal to null. I'm testing to see if star P is equal to null. And you can just say, hey, you're void. The void version of null? No. 0. Star P would be what? The value void. You can't dereference a void pointer. So you have to cast this to be like something like a char star. And then you can dereference it. And you say, hey, are you null? If you're null, then we got to fix you up, which is to say P star is going to get this value. But we have to do again a char star here of P. And here, I have to take the dereference of P. Or I could say your UN. Yeah, let's do UN. Let's do that instead of char. Whew, this is taking forever. UN64T. We're gonna say, hey, you are now that, and I'm going to dereference you. Zero. Okay. So that math should still work. Current value at star star P. I think I should say star star P like that, because that's kind of what we're doing. Writing to star star P. Then here's going to be the same thing. Okay, let's see if we can get that to work. Make. Okay, we got 18 stored here. What's 18? It's 24. Okay, so the offset's correct, but we didn't write the value. I would have expected 24 off from the base would be 1 or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24. So it would have been right here. This last 1, 2, 3, 4. Yeah, the last 8 bytes. So let's run it again. This time P is null, not reading. So now, at least it detected it. Current value is 39. What the hell? So my pointer math is wrong. Something's wrong with my pointer math. I think what I need to do is say this is a uint, so uint 64t pointer. No, uint 64t itself. uint 64t, and then base, just assign it that way. Okay. Just stop treating p like it's a pointer, because it's not. It's just an index. We'll say d here. P is ld. Okay. Then here, it'll be easy to just say, hey, all of this just becomes so much easier. But we have to now add uint, and this stupid thing, integer, uint 64t. So you have to add base say, hey, treat base as if it's a uint 64t, and then we're going to add it to whatever the value is pointed at p, and then we're going to take that value and we're going to treat it like its own uint 64t pointer, and then we're going to dereference it. So this should be a ld here. And this should be a uint 64t. Okay. That makes a little bit more sense. And then we'll do the same thing here, where we get temp. But now temp is a pointer. So we just need to not dereference it. And it becomes a pointer to uint 64t. And now we can write value to it being dereferenced. All right, let's try that. Hey, 7b. 123. Got it. Got it. 126. 70. That was a lot of work. All right, I'm going to quit out of this. Format supposed to type long, and P is a uint64t pointer. We'll just do P here. Why not? Going for breakfast. Enjoy your day, man. Appreciate you hanging out here. I don't know if any of this made sense to you at all, but I'm pretty happy with it. All right, enough of this. Let's continue reading. How many more pages? I don't have that much left here. So the thing that I was curious about, what I just implemented, was what he was talking about here is making sure that whenever you mount the or attach the segment of shared memory, that you compute pointers that you store inside that memory based up relative to the base of where you attached it, which he made it look really easy here. Yeah, maybe it's just my limited experience with C, but I ended up going with a different approach, which is that whenever I needed the offset, I would do I have this? Yeah. Whenever I needed the offset, I would compute the pointer like this using these uint64t's. So I treated everything like uint64t's for the pointer arithmetic and did all my dereferencing, and it worked out. But it's probably not the best way of doing it. Anyways, move on from that. Okay, shared memory control operations. About 7:30. I want to finish up here. So the shared memory control system call performs a range of control operations on the shared memory segment identified by SHMID. The command argument specifies the control operation to be performed. The buff argument is required by the IPC stat and IPC set operations described below and should be specified as null for the remaining operations. In the remainder of the section, we describe the various operations that can be specified for command. So RM of RU stat set. I'm going to skip past that because I've already used one of those and the other two are pretty self-explanatory. So a shared memory segment can be locked into RAM so that it's never swapped out. This provides a performance benefit since one of each pages of the segment is memory resident. An application is guaranteed to never be delayed by a page fault when it accesses the page. There are two SHM-CTL locking operations. SHM lock operation locks a shared memory segment into memory. SHM unlock operation unlocks a shared memory segment, allowing it to be swapped out. These operations are not specified by SUSV3, and they are not provided on all Unix implementations. In versions of Linux before 2.6.10, only privileged IPC lock capability processes can lock a shared memory segment into memory. Since Linux 2.6.10, an unprivileged process can lock and unlock a shared memory segment if it is affected by the user ID matches, blah, blah, blah. Okay, locking a shared memory segment does not guarantee that all of the pages of the segment are memory resident at the completion of the call. Rather, non-resident pages are individually locked in only as they are faulted into memory by subsequent references by processes that have attached to the shared memory segment. Once faulted in, the pages stay resident until subsequently unlocked, even if all processes detach the segment. In other words, SHM block operation sets a property of the shared memory segment rather than a property of the calling process. By faulting into memory, we mean that when the process references the non-resident page, a page fault occurs. At this point, if the page is in the swap area, then it is reloaded into memory. If the page is being referenced for the first time, no corresponding page exists in the swap file. Therefore, the kernel allocates a new page to physical memory and adjusts the process's page tables and the bookkeeping data structures for the shared memory segment. An alternate method of locking memory with slightly different semantics is the use of mblock, which we'll describe in section 52. Shared memory allocation data, associated data structure. I don't need to know this. This is all stuff that is old legacy stuff. Shared memory limits, and these are limits. We don't care about limits. It's good to know for documentation purposes, but I don't care about that. So shared summary. Shared memory allows two or more processes to share the same pages of memory. No kernel intervention is required to exchange data via shared memory. Once a process has copied data into a shared memory segment, that data is immediately visible to other processes. Shared memory provides fast IPC, although the speed advantage is somewhat offset by the fact that normally we must use some type of synchronization technique such as systemv semaphore to synchronize access to the shared memory. The recommended approach when attaching a shared memory segment is to allow the kernel to choose the address at which the segment is attached in the process's virtual address space. This means that the segment may reside at a different virtual address in different processes. For this reason, any references to the address within the segment should be maintained as relative offsets rather than absolute pointers. Further information, exercises. We are done for the evening. Chapter 49. 10:16. Just gonna write that down here. I'll get out of that. Say 10:16 at, what is it, 7:42. And write that out. Get status, CD. Actually, yeah, let's add all this stuff. CD chapter 46. Cat get ignore. No get ignore. There's nothing in here. Chapter 48. That definitely has a dot get ignore. And we'll just do a make clean just to be sure. And then we'll get status, get add chapter 43, chapter 44, chapter 46, and chapter 48. Get status. So we got update to the message queue thing, a get ignore, some design doc, a go file. Yeah, and some other things. I'm going to CD in chapter 48, and we're going to mv main.go. Actually, cat out main.go. This is just the increment thing. I'm going to remove that. I don't think I need that. Get add chapter 48. Get status. Yeah, there we go. So just want to make sure, yeah, everything's C, makefile, get ignore, text. Looks good. So we finished chapter 48. We're on chapter 49. So it's going to be get LGA 3, get CI. We're going to say finish chapter 44, 45, 46, 47, 48. Because we are on 49. And we left off on finishing 44, so we did these chapters today. 45, 46, 47, 48. And I forgot to update the README, so let's do that now, and we'll amend the commit. So we got 45, 46, 47, 48, 49. And then we can go over here, blow away all these. This is going to be... let's go back to our table of contents here. Okay, so we had our intro to systemv IPC, which is 45. That's done. 46 is systemv message queues. 47 is systemv semaphores. 48 is going to be systemv shared memory. And then 49, which we'll be working on tomorrow, will be memory mappings. Okay. Looks good to me. I'm also going to add to the README some other appendices here, because there are ones that I want to read, like tracing system calls. Appendix A. Tracing system calls, that's a small one. casting the null pointer. Let's throw it in, and if we don't want to do it, then we won't do it, which is the kernel configuration. Let's just take a look at it. We got the book right here. So, kernel configuration. It's just a couple pages. Happy to read that. Okay. Git add readme and git status, git ci amend, no edit. Git show stat. Looks good to me. 43, 45, 46, 47, 48. Okay. Git push. And then we can look at GitHub and hit refresh. Cool. Making progress. I should really pad these so that they're sorted alphanumerically. Because they're sorted alphanumerically on my screen here, but yeah. I don't care that much. Alright. So tomorrow we will be starting on memory mappings. I just want to figure out how many pages I read today. So if I cat up progress, Python, we ended on 10:16 minus started on 9:21. So that was 95 pages we read today. Some of it we skipped over because it wasn't really important. But important thing is that we're making about 100 pages of progress a day. Okay, so tomorrow will be memory mappings. What else? That's all POSIX stuff. Here we go. Memory mappings, we're going to go all the way to like 1117, which will be here. POSIX shared memory. So memory mappings, virtual memory operations. Introduction to POSIX IPC. And then we go POSIX message queues, POSIX semaphores, POSIX shared memory. So same thing with System V except POSIX this time. File locking. Okay. So basically to do the same thing that we did today, except we're going to add 2 more chapters. I don't think I'm going to be able to do the whole thing, to be honest. So we'll see how far I get. I'm not going to push it. I feel it every day that I push it that I'm just like starting to burn out. So if I just get 50 pages read, so be it. But yeah, I'm excited tomorrow to read memory mappings and some of the POSIX stuff. Cool. All right, I'll be on tomorrow morning.